and thank everyone for coming. Yeah, you're so many. So yeah, I'm Francesco. I'm a final year PhD student here at the IOA, and today I'm going to tell you about unveiling the first stages of planet formation. So, is this working? No, it's not. Okay. Not okay. Okay. So yeah, sorry. Let's start from the solar system. So until about 30 years ago, the only planets we knew about were those in the solar system. And as you can see, this can be divided into rocky planets, the innermost ones, so Mercury, Venus, our own planet, the Earth, and Mars, and the gas giants further out, Jupiter, Saturn, Uranus, and Neptune. Roughly from 1995, since the very first discovery of an exoplanet, that is to say, a planet orbiting a star other than the Sun, more than 5,000 other exoplanets have been discovered that are shown here, popping up by the year of discovery. Here in this plot, let's see if the pointer works. Yeah, it does. You can see here on the x-axis the distance of all these planets that are shown as gray dots from their own Sun. And, on the y-axis, the mass of these planets. And, there are some figures for the solar system planets as well. What you might notice is that compared to the solar system, those planets look quite weird. And actually, this is in part due to the fact that some planets are easier to detect than others, but also to the fact that some intrinsic differences are there. You can see, for example, that there are planets up here that are as massive or more massive than Jupiter, this guy, but they are much closer to their star than Mercury, the innermost planet in the solar system, is to our Sun. And actually, they're so hot that we call them hot Jupiters. And we need actually to introduce other classes of planets called warm and cold Jupiters to, basically represent all those planets as massive or more massive than Jupiter and Saturn, and orbiting roughly at their same distance from their own Sun. But by far, the most represented category is this one, that of super-Earths or mini-Neptunes. Those planets are a little bit more massive than Earth, but also less massive than Neptune, and so they're called by these two ways. So some of the questions generally people ask when looking at this plot is, how are those planets like? Can we walk on them? Are they rocky or made of gas? Are they small, big? Can we breathe there? Can we live on them? Do they host life? Well, I think actually that the only way to kind of put together all these questions is really understanding how they formed, because their formation history tells us a lot about the properties of these planets, and is, actually what I'm studying here in Cambridge. So how did those planets form? To get a hint to answer this question, we can take a step back and observe the solar system again. Something you might notice is that all these planets are orbiting the Sun on the same plane. We say that they are coplanar. And this was noticed about 200 years ago by these two people, Kant and Laplace, who actually proposed that the way these planets formed was through a very thin disk made up of gas and small dusty particles that at some point clumped together. This disk was orbiting a very young Sun, and for this reason they called it a pre-solar nebula. Turns out that their explanation is quite similar to what we believe today. Nowadays, we know that planet formation is sort of a consequence, a byproduct of the star formation process. And here I'm showing, how stars form. The journey starts from these fuzzy envelopes called giant molecular clouds. They're made mostly of gas and tiny dusty particles by a small fraction, about 1%. And within those clouds, there are some regions that are very dense and start collapsing on themselves. This collapse basically brings about an increase in the temperature, and at some point the formation of a baby star. We call them protostars. Pretty much like babies, baby stars also are always starving, and they eat all the material from their parental cloud, first through these fuzzy envelopes, and then in the form of a disk. This is, as I told you before, a thin disk made up of gas, and that also inherits the small particles that were present in the parental molecular cloud. We call these disks protoplanetary or planet-forming disks because we believe that at these stages, the tiny dusty particles that were present in the original cloud start clumping together and forming planetary seeds and then planets. Those disks live about 3 to 5 million years, and at some point they completely disperse and leave behind planetary systems similar to the solar system. So, as I told you before, we can observe planetary systems. We're pretty good at doing that. But can we take a step back and also observe protoplanetary disks to understand how planets are forming in them? So it turns out that the answer is yes. And to explain you how we do this, I will first tell you about the electromagnetic spectrum. So every object in the universe, including me and yourselves, is emitting light just because of temperature. And, well, light then travels through the universe in the form of a wave that is depicted here in red. And this wave can be characterized by a number. It's called the wavelength. That is the distance between two close-by peaks. So objects of different temperatures emit light of different wavelengths. So if you want to observe something very hot over here, you need to build a sensor that is sensitive to very small wavelengths. And if you want to observe something very cold, you need an instrument able to see very long wavelengths. So our own eyes are an example of an instrument. For example, they are visible to a tiny patch of the electromagnetic spectrum called visible light, this part over here. And in fact, if we turn off light in this room, what we will see is just dark. But using, as it is called, an infrared camera, a number of phases will pop by. Why is this? So the reason is basically that people, unless you have a fever, emit roughly at 36 degrees centigrades. And, well, light emitted at this temperature is in the infrared and cannot be visible by our own eyes. Turns out that protoplanetary disks, are even colder than people, about 300 degrees colder. And to observe them, you need to build an instrument that is sensitive to light in this region that is called sub-millimeter or millimeter. Our infrared thermal camera, our thermal camera for protoplanetary disks is called ALMA, the Atacama Large Millimeter Sub-Millimeter Array. So why this name? Atacama is the place where it was built, the Atacama Desert in Chile, one of the driest places on Earth, about 5,000 meters above the sea level and perfect for astronomical observations. Well, large doesn't really need an explanation. It's huge, you can see it. And millimeter sub-millimeter tells us about the wavelength range, so the kind of light it can see. It's also called array because you can see that it's made up of several modules. They're called antennas, scattered around the ground in some sensible way. So why would you build something like that and not just a huge mirror or camera? Well, the reason is called interferometry. So if you want to observe an object of a given size, your telescope must be of some size that is determined by the wavelength you want to observe at. And for disks, we know that this wavelength is millimeters, and so we need roughly to see them at their size, a telescope as big as 200 meters, which is huge. It's very difficult to build something like that. However, if you build lots of antennas and make them talk to each other, lots of smaller antennas, and make them talk to each other, it's like building a telescope that is as big as the maximum distance between these antennas. So it's an easy way to solve this problem. ALMA is made up of 66 of these antennas, and their maximum distance ranges from 150 meters up to 16 kilometers in the desert, which is great. It's much better than everything done before. And actually, ALMA was a complete game changer in the study of protoplanetary disks. This is how a protoplanetary disk looked like before ALMA. You can see it's a kind of blob, not very well defined. And, the color scale is telling us about light coming from the tiny dusty particles in the disk. And you can see that it gradually fades towards the edge of the disk. However, when ALMA came online and observed this disk, it's called HL tau, is one of the closest and brightest disks. This is the image that came from ALMA, actually. And you can see that it's not a blob anymore. Because of the maximum distance between ALMA antennas, the telescope is actually able to see very tiny details in this disk. And yeah, if you go through its radius, you can see that it's characterized by a sequence of these very bright and very dark rings. And people generally call them gaps when they are dark and rings when they are bright. So when astronomers first saw this image about 10 years ago, they started thinking about the possible explanation for these gaps and rings. And actually, there are so many, but probably the most tantalizing one is that planets, or should I call them protoplanets, so baby planets still forming and eating material from their disk, are actually carving this gap while moving around the star. HL tau is not the only disk that shows these gaps and rings structure, but there are many more. This is another example. It's called D-sharp. It's a family of disks. And, well, actually, most astronomers believe that if you observe these disks at high enough precision, almost all of them show this sequence of gaps and rings. Actually, there are also fancier structures like this crescent over here, where this disk showing spirals. So they're very nice indeed. And, well, so as I said, those gaps are probably carved by planets. But the question is, are you sure? Can we see planets in these gaps? Actually, the answer is yes, but only in one case. This is the only disk where we found planets in gaps. This disk is called PDS-70. You can see it here. And it's characterized by this very bright ring and a huge cavity where 1 and 2, the other is here, you can see it better in the insert, 2 Jupiter-like planets. Actually, they're more massive than Jupiter and they're still growing, have been detected. So this one in particular is very interesting because it's surrounded by this fuzzy envelope of gas and dust. We call it circumplanetary disk because, well, it's orbiting the planet, but also we believe that this is material that the planet is eating and also material that will form the moons of these planets. So why is this the only case where we detected planets? Actually, the reason is that more than a gap, this is a huge cavity, completely devoid of material, where the light from these planets can shine out. But if you look at the other disks, well, most of them are characterized by these small-scale gaps. They're very small. And any planet that would be present there would be completely outshined by the ring nearby. They're much more luminous than the planet. And this makes very, very difficult to understand if there's a planet there or not. So people had to come up with other solutions. And one of it makes use of the Doppler effect. So I'll try and explain what the Doppler effect is with this video. Cool. So when a source of light is moving, depending on the relative motion of the source of light with us, we can detect a wavelength of different kind. In particular, if we are staying at some place and the source of light is coming towards us, you can see that the wavelength we see is much shorter. And we call this blue shifted wavelength. Instead, if the light source is going away from us, the wavelength we see is much longer, and we call this red shifted side. If you think about it, it's something we make experience of in everyday life. For example, when you're walking down the street and you see a car that's honking maybe, when the car is moving towards you, you hear a higher pitch, and when it's moving away from you, you hear something like a lower pitch. Maybe I can... Do you hear it? Ah. Pretty much. Okay. We can see this effect in protoplanetary disks as well. So how does it work? You may remember that planets in the solar system are moving around the sun, and so is the gas and the tiny dusty particles in the disk. They're all moving around their baby sun that is forming. And actually, gas is made of different molecules, and each of these molecules leaves us a fingerprint in the electromagnetic spectrum. This fingerprint is called spectral line or emission line. Here I'm showing the case of carbon monoxide, a very abundant molecule in protoplanetary disks. So if disks were steady, not moving with time around their sun, what we would expect is something like the blue line, so very centrally peaked and very narrow. But actually, since the disk is moving, what we see in our observation is something more like the gray line. So this kind of M-shaped structure, where there is a side that is red shifted and a side that is blue shifted, just because part of the disk is moving away from us and the other side is moving towards us. And we can use these two peaks to understand how the disks are rotating. Here I'm showing the case of HD 163.296. As you can see, we like giving very strange names to these sources. And here on your left, you can see the emission from dusty particles in this disk. And on the right, the emission from gas, the CO I was talking about. And the red part is going away from us, while the blue part is coming towards us. So you can imagine the disk rotating this way, clockwise. Actually, those disks are not rigidly rotating at the same velocity, but the parts closer to the center over here are rotating faster, and those away from the center are rotating slower. And actually, if you take your emission line of CO, like the one I showed you before, you can kind of divide it into small chunks associated with a given velocity. And when you do this, you can sort of map these regions to the part of the disks that are moving at that velocity. So very slow moving regions are those plotted in green, close by to the disk minor axis. Slightly faster moving regions are those ones. And even faster moving regions are much, much closer to the disk center. Actually, those chunks are called channels. And when you have very, very good observations, like only ALMA can give, you can create very, very small channels and kind of continuous plot where, like this, where you're scanning through your line and the plot is showing what region of the disk is emitting at a given velocity. It's very entertaining, actually. It's called butterfly plot, just because it looks like, butterfly beating. So what I'm showing here is one particular channel. So this is just the region of the disk that is rotating at about 1 kilometer per second with respect to us. And you can see here in the bottom that it looks like more like an arc. Well, here on the top, it shows something strange. It starts like an arc, but then kind of goes back and forth again. We call this, in jargon, a kink. So you can see this is smooth, and here it turns around, kind of. Well, what we see down here is what we would expect. And what we see up here is actually something strange that needs to be explained. And actually, people propose that an explanation for this kink is the presence of a planet in this disk. And what astronomers do to test their hypothesis is running numerical simulations. So they put some numbers into a computer and compare the data they have to a number of different models. Here, this model was run using a planet like Jupiter. This one is for a planet twice as massive as Jupiter, and this one is 3 times as massive as Jupiter. And what you can see that here the kink is barely visible. Here you can clearly see one, and here it's much more clear. So, yeah. Actually, you can use this comparison between data and models, not only to understand if the reason of this kink is a planet, which seems quite the case, but also actually to weight your planet. So, yeah, getting back to the original plot of all the exoplanets in gray And here, their distance from their own sun, and here, their mass. Here I'm plotting the 2 planets we discovered in PDS 70, the big Jupiters in the gap, and also the 2 new planets that have been detected using the Kink method. And actually, well, you can see that they're different because these 2 are very young, these 4 are very young, and the others are much older. But also because, well, our detection methods are very good at detecting very massive planets, very, very far from the central star. Actually, the future is bright because many, many more data are coming, and many more planets like this will be detected, really kind of creating a small family of young planets we can use to understand how they evolve into the much older ones we see today. And yeah, thank you for listening.
Additional questions? Wonderful. Okay, well, do we have any questions for our speaker? We're still just setting up outside for a little bit. Okay, we're going to do questions featuring the roving throwable microphone, which is very exciting. Also featuring my terrible throwing skills.
Haha, 1, 2. You said that one side of the disk is moving 1 kilometer per second or something towards us, and the other side 1 kilometer per second away, or a day, whatever it was. But the center of mass is presumably also just got a relative velocity
Yeah,
with
that's
respect to us, possibly much, much more? Or?
Yeah, it's generally we don't like the offset, so the velocity of the star, so we subtract it and just count everything compared to that velocity. Yeah. Because we are just interested in the relative motion of the side going away and the side coming towards us. Yeah?
Any more questions? Okay, right to the back. Okay, I'll do you first, and then maybe you pass it back. So when you talk into it, just talk into it like this. Your mouth's got to be quite close. You ready? No, I'm going all the way. Oh. No, it's good. Right into the black side.
How old can a planet get before it goes out the disk?
So yeah, it's a very good question. Actually, it depends a lot on the planet and on the disk and where it is in the disk. So I'd say more or less 5 million years. Yeah, it's about the age of these planets here. These 2 are about 5 million years old, and all those ones are much, much older, a factor of, yeah, about 1,000 more, yeah, giga-year-old.
I think there was someone behind. Do you want to pass it back? Do you have a question still? You do. Okay, do you want to pass it back to that young man there?
Sorry?
How old is Jupiter and our star?
Oh, yeah, 4 billion years. Roughly, 4.6.
Yeah, can we get it back this way? Yeah. Do you want to pass it back over here? Yeah, just like aiming over here. Doesn't this lighten up questions?
How old?
A lot. So yeah, every star forms with a disk around it, and there are billions of stars, billions of stars out there. So all these stars have formed with a disk. They don't have a disk anymore, though, but still, so many stars are forming with lots of disks.
Okay, you want it? Oh. The throw was worse than the cat.
Do you know how many planets could possibly be in a disk?
It's another very good question. So it depends a lot on the disk. Let's go back here. So you can see that they're all different from each other, right? So for example, this one is a pretty famous one. And well, when looking at the emission from the tiny dusty particles, people at the very beginning started saying, okay, for each of the gap, you have one planet. And here you can see 1, 2, there's actually a third one, a fourth one, and a fifth one. So potentially up to 5 planets. Actually, it was shown recently, well, not very recently, that actually, if you just have a planet, if I don't remember if here or here, just one can explain all the features you see, which makes very complicated to understand how many planets are there just looking at this figure. But maybe just one, potentially a lot.
Cool. Do you want to pass it behind you? 2 rows back.
That
Oh, sorry, I didn't get the question.
Maybe just forget the box and shout.
So you said this were thin. I was just wondering how thin is thin, and is there much variation?
Ah, okay, okay, the thickness, okay. So we say that, so at about 1 AU, the distance of Earth from Sun, the disk could be a factor of 1/100 thick, basically. So yeah, 0.01 AU, more or less. Yeah.
Okay, time for one last question. If anyone's got one, okay, right to the front. Okay, you. That was the best throw of the night. There you go.
The other elements in the disk without the hydrogen and helium, what do we have?
So there's a lot of hydrogen. Most of it is hydrogen. The problem with hydrogen is it's very difficult to observe. We cannot see it. But there are lots of molecules, actually. Other than carbon monoxide, you have any kind of, we call them prebiotic molecules, or those molecules that form the DNA and then in principle can enable life. You have water there. You have really lots of molecules. Yeah.
Wonderful. Okay, well, first of all, a big hand for our speaker.
Thank you.